I'm sure you must have heard about heaps and priority queues, maybe together, maybe separately, but let me tell you that they both do the same job. They're both referring to the same data structure. Now, priority queues, as the name suggests, gives priority to some elements in comparison to the other elements in your queue. So queue could be like just a list of some values, and you are giving some priorities to some elements, so they are like right in the front, or you give them more preference. They reach the front first, and there are some elements waiting for them. Now heaps is specifically like let's say min heap or max heap. They also give priority based on if it is a min heap or a max heap to its values, right? So right now I have written this heap, but it's actually not heap. It's let me just change it to like a regular array. Let's call it array or a. So now this array that you're seeing right here, let me write it a little closer. This array that you're seeing right here, now this could be simply represented into this binary tree. How? We could simply have our these root calculated by basically I will be my root. This is my root, and then this root will have left child and right child since it's a binary tree. So it's going to be 2 into I plus 1. That is my left child, and 2 into I plus 2, that is my right child. So now let's see, how did we, like I'm just showing like how we converted this array into this binary tree. Just for the representation in memory, when you are heapifying something or you're creating a min heap or a max heap, the computer is storing it like as a list and just doing its calculation using the list, because there is nothing like this structure, unless you create one. Because if computer can do the job like just using the indexes, then why not? So here let me just show you like how we calculated it. So let's index our elements right here. So this is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have 10 elements right here. Now our root will always be present, like the root of our binary tree will be present always at the 0th index. So 2 right here, that's the root. Let's take this as a 0. So now how do we calculate the right and left for when the root is 0? So let's calculate its left and right child's position or index. So we will be doing it 2 into 0. So root is 0. So left child would be 2 into 0 plus 1. That's the left child's position, which is 1. So 1 index, if you see right here, so this is the left child, this is the left child. You can see 5 is the left child, and then let's calculate the right child. It's going to be 2 into 0 plus 2. Now that will give us 2. So now you can see that 0 is present at the second index. So this is my right child for my root, which is 2. Now and same way we can convert for 5. 5 is present at one index, so where it's going to be its left child and right child. So we can do the same calculation for 5. I'm just going to do one more, and then we know like what we are actually trying to do. So that will be 2 into 1 plus 1 and 2 into 1 plus 2. So this will give me 3, and this will give me 2 into 1. 2 plus 2 is 4. Okay, so 5 is right here. 5's left child is 1, which is present as third index. Left child is 1, and right child is 10, which is present at fourth index. So now you can calculate the position of left child, right child, parent position, whatever you can calculate for this binary tree. So what I was really trying to show is that we can represent this array into a binary search tree. Now how do we convert it to a heap? Well, in Python we have a library that's called heapq. That's the data structure, heapq. So we will be importing heapq, and then we can perform some operations on heapq, and one of the operation is basically heapify. So heapq, once you import heapq.heapify, and if you are sending in your array right here, and basically this should be giving you a heapified. By default it gives you a min heap. And what does min heap means? Like you'll be converting this to basically restructuring your binary tree, so that the most valued, which is basically most valued values go on the top, and then the least values are on the bottom, which it really means min heap means the minimum value should be on the top, right? So once if we convert this in Python, and the same concepts can be used in other languages as well, but like we are doing it, specific to Python. So what really gonna happen is if we heapify our array, this will restructure our array into looking something like this. This will perform some operations, and those operations are basically shift down. So what it's really going to do is it's going to push up the least values on the top and push down the bigger values on the bottom. So we'll go into that, but like just let's go through what really happened here. So the minimum value just came on the top. Minimum value is -4 in this entire array. That's right on the top, and it's on the 0th index, which is the root of our binary tree. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So now if you want to pop something, like if you want to, because that's the reason it's called heaps and min heap and priority queue. The reason is like you have given priority your minimum element and it's sitting right on the top. All right. So because it's sitting right on the top and right in the front of your heap queue, if you want to access the minimum element in your queue, so what you will do is you will do a pop operation. You will do a heap pop operation. So just like here we did heapq dot heapify, and then you provide your array right here. Same way for heap pop, you will be doing heapq. By the way, first don't remember to import this. You have to import it, and then heapq dot heap pop, so 2p, remember this, and then you provide your basically the array. So this will give you the minimum element, and this will pop this 4. So like what if we really pop this 4? What happens if we pop it? So popping this will just take this away, it will pop the element, it will return it. Then we have just broken our binary tree, like we have broken our heap. So what's really going to happen now? So what will happen is the minimum element. So what really happens behind the door is this element right here will take this position. This is how things work, and then again we'll perform a heapify, and in that heapify we will basically keep pushing this element to its right position, and so that like the minimum element gets on the top. So but let's say what really gonna happen now is we decide which value from these two will take place here. So from 1 and 0, this is the minimum, right? This is the minimum, so this minimum will go over here. Then this position is empty, so what will happen is out of 3 and 2, this position will be taken by 2. Now this 9 will basically come over here. All right, this 9 will come over here. Now again, this is converted to again min heap. Remember initially when we just heapified it, it performed in big of n time, it performed heapify operation, which uses something called push down. So it's pushing down the bigger element to the bottom, and you can do same for the max heap. In max heap, what you really do is you negate your elements right here when you are heapifying it. Okay, so now how about heap push? Heap push meaning like you can push some element to your heap. So let's say if we heapify, same thing is going to happen. It's the same way we will be adding this to our heap. So heap q, heap push, so double p. And what do we want to push? So this is the array we want to push to, and second argument will be the element. So we want to put, let's say I want to push I would say like I want to push maybe 6. Let's push 6 into our min heap. So what's going to happen now is, since we are pushing 6, so we'll create basically a node. Let's call it 6. Now initially what really happens is like you append this to basically the you go to your left child, keep going to the rightest of your left child. So this is that position. What you're going to do is you append it right here, but we're going to figure out like if this is its right position. It's not. So what we do is we will bring this 9 over here and then take this 6 over here. This 9 takes its own place. Now is this 6 in the right position? Yes, it is. So I guess like that that is its right position. Otherwise we will keep pushing it on the top wherever its right position is in comparing to its neighboring values. Then you can do a heap peak. Heap peak is basically you just want to peak the value on the top, so you can just take a peek of this, which is basically you can access this by min heap -1 value. Okay, so not -1, so I'm sorry, it's like the 0th. So you can do heap q dot heap peak, and it should return this value -4. Okay, well, -4 is not present here because we removed it while understanding things here, but you know what I mean. And then remember, I'm sure you remember this heap sort algorithm. That's where it comes from. What you really do is, once you have your heap right here, your heap right here, you keep popping the minimum element from your heap. So you have this, let's say this unsorted array in the beginning, you had that, you convert it to your heap. Now minimum element should be on the top. You pop that element and create your array, so 0. So maybe what I'm really trying to do is, heap sort works in a way like you converted your array into min heap, then you pop the first element, the 0 will come here. Now again, if you're removing 0 from here, this 1 will take this place, this 1 should take place of this 0. Now out of this 5 and 10, this should come over here. Now again, what do? You again gonna pop, so this 1, you again pop it out, so that's gonna be your second value. So 1 right here. Now out of 2 and 5, this 2 will take place on the top, so this 2 will come over here, this 2 will be right here. And then out of 6 and 3, this 3 should come over here. Out of 8 and 12, this 8 will come over here. Now you will again pop. So now I guess you understand what I'm trying to say. Then you will pop 2 again. So this 2 is out, this 2 is out, right? This 2 is out, you popped it. Now out of 3 and 5. So this is how you perform a heap sort. And because you are doing it for all the elements, and each time you basically pop and rebalance your tree, because you have just popped your one of the elements. Now it will take basically the height time, which could be worst case, it could be n if it's really unbalanced, and that's how you are going to have like a big of log n is the height, and this is basically you're doing it for all the element. That's why its time complexity is big of n into log n. Now we have understood heap, min heap, max heap, and you can do the same way. Max heap, you just need to negate all the values and then heapify it, then it will give you a max heap. All right, now let's see how it must have actually converted, it must have performed the heapify operation. So what really happened is, in the beginning we had this array, this array. This is not this is not the heap. This is this array I'm talking about. This is the array. Let me copy this, and let's copy. Okay, and let's paste it right here. Okay, so this is the array that we are working with. This is the array right here. So this is not a heap right now, but let's convert it. Let's perform the heapify operation on it. How do we do it? Now, in order to heapify, it's going to have something called push down or push up based on its min heap or max heap. It will perform the very first operation. It's going to go to all its elements, and then especially, let's not go to leaves because it doesn't really need to decide over there, but let's go to first known leaf from the bottom, which is, let's say, this one right here. So this one here, it's in right position. This one you see right here, this is in right position. This 10 here, it's not in its right position because its child has to be greater than itself, because our root needs to be smaller, all right, because it's a min heap. So we're going to rearrange it like this. Then we come to 8 is already done, -4 is already done. Then we're going to come again here at our 5. So what will happen is we'll push 5 down, we'll take it out. So we'll take it out, and then this 1 should go up, take its place. This will come right here. Then in the next one, 0, -4, this negative should be going on the top. This should be going on the top right here. Now you go to the root, then you decide this 4, -4 should be on the top, and this 2 will come down here. But you're not done yet. You will keep performing this operation again and again until you are out of basically you cannot change your array anymore. So unless you can change, you can make the decision to change your structure, you will keep doing it until you have the minimum element on the top and its children also both smaller than itself, and then that basically satisfy for all these little cute binary trees you can see right here. So it should be satisfying this as well and this whole as well. All right.